go ahead and get started. I noticed the audio quality on the recording from Tuesday was not very good. I think I can stand, I can move around. As long as I stay in this general region, you can hear my voice pick up, but once I walk over there, it completely drops out. So I will hover here, and I think we can make things work for recordings purposes. And obviously several of you who are not here will hopefully want to view the recording. I was monitoring kind of remotely the MP1 progress in lab and chatting with the TA as well. I'm a little concerned, I guess. I mean, concern is a big word, but I don't know how far along people are. Does anyone have anything drawing on the display yet? Anything? Okay, what are you drawing?
I mean, I just have the OpenGL. I don't have any hardware.
Okay, so it works on the workstation. You have a little app that you can use. Anything on the hardware attached monitor, the FPGA's monitor yet? I think I know the answer to that based on, unless there was some radical progress done yesterday afternoon and early evening. Demo day is on Tuesday for MP1, and I would think getting anything on that display hardware is about the halfway point for MP1 in terms of making progress, because that's showing that you have an end-to-end flow of data, and that is necessary, I would say, but not sufficient for getting through MP1. You still have to have a deep understanding of what's happening on the driver's side. You're going to have to do some pretty low-level debugging unless things just happen to work exactly right the first time you do that end-to-end pass. I think you've now seen some of the challenges, or maybe you could think of them as limitations of doing simulation for these cores in isolation. Your simulation is only as good as your test bench for any of these individual cores. It'll allow you to test certain things, like does it come out of reset properly? Does it progress through states in a state machine properly? You can't simulate, at least with this system as written, that to check that the entire end-to-end graphical flow is working correctly. So you have to start relying on other tricks as well. Assuming your simulation looks as good as you can determine that it looks, you then next have to look at what kind of debug information can I get at runtime out of my design? Can I add additional software accessible registers like we talked about on Tuesday to check the current status of various internal variables in my design? That gives you some level of introspection. There's also this other component you can add to your block diagram called an ILA, the Integrated Logic Analyzer. And that is very useful for monitoring bus transactions, the things we were talking about on Tuesday, AXI stream transactions, AXI memory mapped, AXI light transactions. You add one of those modules, you just kind of tap into the existing AXI bus that you're using, and you can check to see, for example, is my render output core ever writing anything to memory? That's an important question, right? I have a black screen, nothing's coming up on the screen. Where are things failing? You have to jump into that kind of debugging mindset of, okay, I have this render output core. I know its responsibility is to write things to the frame buffer. What the ILA can tell you that otherwise can be hard to sometimes monitor is the render output actually getting any input data, or is something else stuck? You can add an ILA to the input AXI stream to that component. Is it actually getting any data in the first place? Or use your debugging registers. Am I actually writing to memory? You can add another ILA connection to that AXI memory mapped interface that says, okay, here are the write requests, here's the addresses that they're happening at, here's the data values. Maybe the writes are happening, but the values all happen to be 0 because you have some small mathematical error in the color calculation. Or maybe the address calculation is just off enough that while it is writing a whole bunch of things to memory, it's just not in the perceived frame buffer location that we're expecting. You got to get to that mode of debugging pretty quickly today, tomorrow, so that you can still kind of get the rest of it done and have a successful demo day for our Tuesday. And teams kind of tell me, I know not everyone is here, this isn't fully representative, where you are at right now, what's left to be done, what testing is need to be done. I'll start front row. What do you guys need? Lots of things, I'm sure, but what do you got?
Lots to do. We're still working on render output. Render output file.
Yeah.
Still not working. Those you guys mind?
What does not working mean to you? I mean, okay, I understand. Not working is not working, but like, what's left? What do you need to do to get it
We had
working?
some mega weird compile issues with the issue.
Okay, so something syntactical that wasn't valid.
Not figured out for a while.
Okay.
So we tried a different version. I think it's good.
Okay. And I would also argue, one way you could kind of fork your design to continue to make progress is you could have a version of your render output, and it's really just the one VHDL file you're versioning and changing anyway, right? One version that always writes green pixels to the screen or something kind of trivial, right? Just to confirm that the rest of your system is working correctly. or that, once you have the rest of the system working and render output, you can connect it together. So you don't always have to wait, well, I can't do anything because, well, this person on my team doesn't have their stuff done. There's always ways you can kind of continue to make progress so that it's not exactly blocking each other. But I understand the desire to get those cores fully working and then start the testing. But that's not even quite the halfway point, having all those cores fully working. How about other teams? Ben, how's your team doing?
We just got it to where we have reason to hope, based on the simulation, that it will work. So
Hope is not a strategy, but that's fine. That it'll work based on simulation results. And as we talked about briefly just on Discord, right? Simulating the render output core is a little tricky. Unless you're simulating the full system, which has its own difficulties of getting valid data in and out of the simulation, you can simulate up to the point where you're expecting some response from the other side of the AXI transaction, right? And generally, one of the first things that cache core will do on reset is it'll flush the cache, and that may itself be triggering a bunch of AXI transactions. And it's a write allocate cache. So even if you're just only wanting to write pixels to memory, the first time you try it, it's going to be a miss in that cache. It's going to then try to read data from memory first, so that it can have multiple hits in the cache for successive writes. So it's a little hard to simulate. So unless you have a really clever test bench, I think you can mostly simulate that your logic is doing what it should be doing, that you're progressing from state to state to state, and at the end of it, you're interfacing with the cache, and the cache is doing something, or the cache is trying to access memory behind it. And if you have that, at least then you're at that next point where you can kind of figure out what could be next, what could be going on next. But that would be good to get that done today. That's my recommendation. If you can find time, I'm not trying to scare people or anything, but like get to a point where you think all your VHDL code is basically done. Again, 99% done, is helpful. Maybe there'll be one line you'll change, or one arithmetic operator you'll change, or one register, bit that you'll change. But generally done, and then you really got to get into that debugging and testing mindset, because it's not going to be quick for this, because we can't simulate the full system. You'll be kind of testing the full system, and you have to go into that knowing that each test is going to take a little bit of time, and you have to be able to learn something from each test. So don't make it a binary test. Did I get a red pixel on the screen or not? That's not going to be super helpful to you, because you have to be able to answer, okay, why did I not get something that I was expecting? What component broke down? Where is there a bottleneck? Or where is somewhere there's a break in my understanding between how I think data is flowing through the system and how it's actually flowing through the system in practice. Group 2, you're group 1. Group 2, how's group 2? You said you have a nice OpenGL application, so that's nice.
So I basically make a gradient circle and I can multiple of them around the screen. It sounds
Just
like,
using GL points then, basically?
Yeah.
Okay.
So it should be able to render on the hardware outside. The hardware side, it sounded like from my group members, they have both the IPs that we needed to make it working. They just haven't integrated them yet. That was a goal for this weekend that we're going to work on.
Yeah, it's a good goal for the weekend. Sometimes the Vivado tool is a little annoying about that as well, about, you've made a change to the VHDL file in the sub-IP component. Does it properly get refreshed in your top-level project? I think the documentation may not be perfect on that either in terms of my write-up, but there's a set of steps that seem to work well for me. I tend to have multiple Vivado projects open in parallel, one for the system level, one for the IP core that I'm currently working on. Every time I make a change to the IP core I'm working on, usually then the system level can check that and they'll say, hey, do you want to grab this updated version? And it should be able to then keep commonly, grabbing that updated version. And I also mentioned that my suggested trick would be to have a debug register that just is there to store IP core version information. And it's just some counter that you're incrementing every time you make any change that you want to test in the VHDL core, so that you know, okay, I tested version 22 yesterday, here's my results. I know that I'm testing version 23 because I'm going to print out that number from the driver. It's going to print out that register value, and I know that I'm not testing yesterday's code, because now, given 4 days to get this done, you don't have a lot of time to kind of waste or spend testing stale code, somebody else's code. This is supposed to be a hard course. It's supposed to be fun. Okay, it's always supposed to be fun. That's my goal. I want you to enjoy it. I want you to learn a lot. I think the OpenGL bootcamp will start a little slow, but then I think it'll be fun by the time we start to play around with it. but the labs are supposed to be kind of hard, and so this, MP0 had its challenges, but I think everyone kind of just got a reasonable, good enough version working, and so you may have maybe then underestimated what's coming now with this MP1, and MP2 is a little harder than MP1. So you got to find the time as a team. There's no quizzes, there's no exams. You don't even have to show up to class apparently, right? So there isn't that much in this class other than working on this major like lab experience, right? So I want you to find the time for it, right? You have other classes, other projects, other things going on. But as a team, it's good to have a plan, but that plan probably needs to be a bit more aggressive if you want to succeed with MP1. Okay, so that's me trying to scare you. Today's topic, where we're getting really started, is learning more about OpenGL. I think the truth of it is we can't cover all of it. As we look at the API, it's quite massive. It's sprawling. There's lots of uncommonly used features. Our goal is also not to become necessarily expert graphics programmers, and there's whole courses that teach graphics programming. And even one such course is nowhere near sufficient. It's like saying you took one, programming course and you know everything there is to know about programming. Graphics programming is its own separate discipline, or one scientific computing course. You're not an expert in that either. So I think, my role, our job here is to get everyone to a reasonable level of minimum, familiarity with it. And that since we're very rarely starting with just a blank slate when we're doing our OpenGL programming, you'll have enough understanding of what we already have in place to make changes, to be creative with some ideas of your own. And I think we'll be able to accomplish that. And we can do that, a big chunk of that today, and maybe then finish that up on Tuesday. Yes, question? Sure.
I know there's a CS course that kind of goes into graphics programming. Is that like the only one?
There's also one that mechanical engineering offers that also does that, maybe more for modeling purposes as well. The CS course seems pretty decent. It's changed over the years. The last I checked, it was using, I think it was using WebGL, which is a nice technology if you want to learn that as well. I don't think there's any more courses that are learning traditional OpenGL. And then as we'll see here, there's more advanced APIs for graphics that I don't think anybody is covering, because they are pretty new things. So if you learn enough OpenGL in this course, and of course we're doing a ton of hardware design in this course as well, a lot of architecture in this course, that other course may be a nice way to kind of strengthen some of the fundamentals we learned here. But there's a lot to it. I guess I'll be honest with you, and it's something that as you stay on for graduate school, as you want to learn more, there's some fun projects that could be done, looking at either advanced rendering techniques or modern usage of 2023 APIs for graphics. We are reasonably modern with this, and we have something that works with our system, so it's good for us. But there has been a lot of advances, and that's part of the point I wanted to make here. We're covering just enough to get you started. Mechanics of OpenGL, of which there is a decent amount of mechanics to learn, then on sort of deep expertise of OpenGL. I wouldn't even necessarily say I have any deep expertise in OpenGL personally. I know enough to get by. I understand code that I read, but those, for example, who make game engines for a living, who really understand that the optimizations and the roadblocks you can run into if you really need to hit some certain performance goals, I've never done that. I don't have that type of expertise. If I were to make a game, which I sometimes enjoy doing, I use an existing game engine, and where you're normally programming at a level above the graphics API, using the game engine's API, which can look somewhat similar in a sense, but I know enough to get by, and I think that should be your goal. By the end of this boot camp, and as you gain experience this semester, there is kind of the Bible that I have up there on Canvas. It's in the library as well if you want the paper copy, and that's the OpenGL programming guide, the red book, mostly covering chapters 1 through 4 and subset of the API calls listed in Appendix A that has a corresponding code repository on GitHub that doesn't work especially well, but I have a version that I was able to get to compile if you ever want to try out any of those examples from the book directly. The nice thing, at least, about our understanding of OpenGL is it's not like a one-shot thing for us. So this is our boot camp. This is so that you're not like totally intimidated by opening up a C file, a CPP file, and editing it for MP1 purposes. But as we're learning more about the algorithms, applications, and the architecture, we'll keep coming back to it. And we'll kind of go back to the same basics of what we're doing with OpenGL. And I think we'll get better with it. We'll get our knowledge updated as we go. And ultimately, I think you'll learn a lot in the lab. So I can talk until I'm blue in the face about this API call at OpenGL and what it's supposed to do until you have to implement the driver call for that. Then you really have to go back to maybe the red book and say, okay, this API spec says that this call should be copying this kind of data. Now, part of the challenge is the API specification doesn't necessarily say how you have to do it. It just says it needs to be done. So there's still some design choices we have. And then ultimately, okay, now I have a hardware module that's expecting this type of data to come through. What does that hardware module expect? Once you've done that 5 or 6 times this semester, I think you'll get a pretty deep expectation for what is happening underneath the hood, even if we aren't like true graphics programming experts, at the end of this course. So graphics API, I've used the term already before, and it's a term I think you would have seen in just your programming experience, right? An API, or application programmer interface, that's a set of functions or procedures that allow the creation of applications, right? So it accesses the features of an existing set of code or set of features in an application or just some other service. So if we have a graphics API, you can think of that as the set of functions that allow us to interface with an underlying graphics hardware and also potentially software implementation. The main goal of a graphics API is to provide the set of functions that allow you to specify what is ultimately needed to form an image. So we have talked a little bit about objects. I've talked about triangles. So how to specify triangles in a scene. We haven't talked at all about viewing, and I don't want you to mess with that yet, but we will start to talk about how do I set that up? How do I set up the virtual kind of camera in my scene for where I'm looking at the object? We will talk about light sources and materials and their interactions as well. How do I determine what color ultimately the various objects should be in my scene? And depending on the type of API that you are using, the API may also specify things like ways to query what the system is capable of or not capable of. Some graphics API also directly include platform agnostic ways of getting input from your devices and specifying the output to your monitor device here. OpenGL does less of that, but there's common companion libraries that provide you exactly that. So most graphics APIs support just a limited set of primitives. Points, you can think of it as a zero-dimensional object. That's what we're doing in MP1. Line segments, so a pair of points, and then we render the line between them. Polygons, we'll be talking about the different types of polygons, and then more commonly, some curves and some surfaces, but not as much in modern OpenGL. All of these different set of primitives are defined through these vertices, the locations in space in which we're going to be creating our geometric objects. This is an example object specification. I put in parentheses here. This is legacy OpenGL, and I'll talk about what that means. I still like using it just for like in-class examples. We don't use this in the code for the lab. It's just very clean and just, very easy, I think, to read and know exactly what it's doing. It's very inefficient, as I think we'll eventually see, but it's just great for just explaining what's happening here. So we have some way of specifying that there is a type of primitive we want to start creating here. In the legacy OpenGL, that was via a GL begin call. We don't call that anymore. But GL begin, we say we're going to start specifying triangles. So GL triangles is still a keyword we use today. We are then going to, in some way, shape, or form, specify color information as kind of a state change. We're saying here is the state of the preceding vertices we're going to be specifying. And while syntactically that's not exactly correct, it's good enough for our purposes on a PowerPoint slide, we're going to say we want them all to be red. And then we're going to be specifying the location of a set of vertices. If it's going to be a triangle or triangles we're specifying, it should be some multiple of 3 vertices that we're specifying here. In this case, we can kind of squint and kind of guess that would be potentially an XY location in a 3-dimensional space of where these things are going to be formed. So we specify X, or X, let's ignore Z for now. XY is 0, 0. That for the first point, the first vertex, the next one is 1, 0, and the third one is 0, 1. We've specified the state as red. What is this going to draw? A red triangle. Would you like any particular kind of triangle based on those points? It's a right triangle. Yeah, there you go. Don't want you to mock red triangles too much in this class. There's a lot that goes into your hardware getting that red triangle to look nice at the end of the day. So I'm not joking about that. So we're going to be doing lots of red and multicolored triangles this semester. the thought is once you have one working, it's not too much of a leap to get two working, and then once you have two working, it's not that much of a leap to get, a million of them working. So that is a single red triangle being specified here. If instead, and you do again syntactically have to kind of squint to accept what's happening here, if instead we were to specify first the current color is red, then we specify 1 point, then the current color is blue, and we specify 2 points, what would this next triangle look like instead? Same location, so still right triangle. What would it roughly look like? I didn't say, but we would assume that this, you can kind of guess, but this would be 0, 0, right? Then this would be 1, 0, and then this would be 0, 1. In reality, it gets a little messier. We'll learn that pretty exhaustively in about a week here. But assuming that this point is 0, 0, this lower left-hand corner of the right triangle here, what would this triangle look like? I don't need a really precise answer.
The bottom left would be blue, and the other two would be red.
Other way around, but yes, right? It would be a reddish blue triangle, right? We'd specify we want current color to be red. We specify that lower left-hand point, and this is also not rendered. This is PowerPoint rendered, but it would be a gradient of some sort here. It wouldn't look too different than that. PowerPoint has its own gradient algorithm. OpenGL does not specify what gradient algorithm you need to use. We have one that we use that makes our hardware relatively straightforward. Actually, there's no guarantee that you could say based on this specification that this arbitrary point at this location in our pixel space should be this precise shade of purple or whatever it is. So, and different implementations would have potentially different values for that. And unfortunately, as we'll learn a little bit more about rasterization, there's many, many different algorithms we can apply to it to determine what that gradient should be. But reddish blue triangle is what ultimately we would get from that type of specification. Part of why the red book is so large, and again, this is legacy OpenGL, and so it's not even in that red book that I have on Canvas for you to look at, but there's very similar types of ways of specifying attributes, as we will learn here, is when we want to specify color, I think if we thought about it, we could think of like 3 or 4 ways of different functions we'd want to write to specify color. There's like 40 of them in OpenGL, and they're all fine. They all do something reasonable. They're just different ways of providing that specification for any attribute, but for color, for example. Same for position. Same for all the other information we want to specify. For the labs, at least, we pretty much say, support this function, this function, this function, and this function. We could have said, it would have been fine, I guess, to say support all 40 color attribute specification functions. From the hardware perspective, it probably wouldn't be any different. Usually, I think the driver would be taking care of that, where this specifies the color as a floating point value, and this function specifies it as like a binary value. This specifies it as an integer range. This specifies it as normalized. This specifies it as this. There's a whole bunch of different ones. My best guess, who knows, in modern systems that aren't entirely open to how they're implementing things at this level, my best guess is, the driver takes care of some sort of data normalization at that point, that it takes input for what you want it to be specified as, converts it to some internal canonical format, then that's all your hardware really then needs to support at the end of the day. So I could have had you do, support all these different functions. There, it's just extra coding. I think you learn probably a sufficient amount by saying, here's the one function for specifying color we are supporting, and here's how it goes from application all the way through. But the limitation and or restriction there is, you'll have a bit of a porting job ahead of you if your desire is to take some existing OpenGL application you find online and to map it to our hardware. It's going to be doable because I think we support a reasonable set of things in our API that we are supporting in the lab processor. But if it's not using the exact same names for the functions that your driver currently supports, you're going to need to refactor it to use our versions of those functions. So there's a bit of a trade-off there. But for now, I think the main takeaway is the API allows us to specify some information about a particular scene that we want to render. You can think of it as the word we'll start using is attributes. What can you tell me about the particular primitives in a scene? For now, the most basic things we want to specify, starting for MP1, is location of where these vertices are in a scene, and for now, what color those vertices are in a scene. This is what I call the legacy OpenGL way of doing things. This is the so-called fixed function implementation of those. We don't implement that in lab. That doesn't work in lab, but it's close enough to what we're doing for understanding what's happening in OpenGL. I'll start jumping back and forth between fixed function legacy, deprecated versus newer version here. So I used the term API already, and I think it's a term you should be familiar with. You will oftentimes also hear GPU implementations and referring to like an ISA associated with them. How many here are familiar with the term ISA? Should be everybody, but that's okay. If it's not, you may have heard it in a course and you don't use it that often. ISA is something that a CPRE 381 or equivalent class should be covering. There isn't that much to cover about it, but it's the instruction set architecture. It is what are the class of operations that this processor or class of processors is expected to support. What are the instructions? What is basically their syntax? And what is their semantics? What are those instructions or those operations supposed to do? Whereas the API is, right, that set of functions and that specify what something else should do, whether it be another piece of software, whether it be a system, or whether it also be hardware. I think in many other contexts, the distinction between what is an API and what is an ISA is pretty clear. API refers to some software library, ISA refers to hardware. When we start talking about OpenGL and graphics programming, I think it's a little bit more subtle because there's this kind of coevolution where the graphics API evolved to support hardware functionality that then co-evolves to support new things in the graphics API. ISA tends to be a lot more low level of a specification, right? An API tends to be, here's the set of function calls you need to support and what they are supposed to do. You will be surprised as you read the OpenGL spec in that red book, what it says and what it doesn't say in terms of what needs to be supported. Whereas ISA tends to be lower level, less so functions, more about what kind of instructions are needed and what are those instructions supposed to do. But as we'll see for GPU and for OpenGL programming, partially because of its evolution as sort of an assembly-like language for graphics processors, a part of the OpenGL API is really telling what does your hardware need to support, what kind of operations, what kind of instructions does your hardware ultimately need to support. That's, I think, a sufficient thing to keep in mind. You may see those terms. They're not interchangeable, but they're a little blurry, the difference between them. I won't talk too much about early graphics history. It's nice to know history, but it's not as relevant today. This started in the 1970s where we're trying to come up with kind of one consistent API that would be in common use. There's GKS system. FIGS was a system that was used by more of the CAD community. What was invented in the early 80s, the X-windowing system, which is client-server architecture, where you're really specifying whole frames of data as well as some events on those windows to be sent over relatively fast at the time. Networking connections here. In Linux today, we're still using, by and large, some variant of that X11 protocol today. That's changing very slowly in Linux. If you ever read any documentation on Wayland systems for your underlying renderer in a Linux system, that is a full-scale replacement of X11. It's taken over a decade. It's just lots of things they want to kind of bake into that. We are still using X-Window systems for our Linux systems that we're remotely connecting to, as well as the ones in the lab. We could support the more modern Wayland renderers, but that would require a full-scale kind of redesign as well. So I'd already talked about SGI briefly as kind of the revolutionary hardware and software company. They created this set of graphics workstations that were extremely popular in their era. They were the first to kind of implement a lot of that floating point math directly in hardware. They had their own internal library that they used. It was called GL, and that was kind of the basis what became to this OpenGL. So there was an internal SGI product, this SGI API called just GL, and then it led to some eventual standardization and referred to as OpenGL. Its advantages, at least initially, was that it was relatively easy to use. Your mileage may vary. And also what it didn't include. It didn't try to be a full-scale replacement for like the windowing system of your operating system like some of these other standards were. So it was independent of all of that other stuff. So you would still need to have code that would do things like create a window and check to see if someone pressed a key on the keyboard or clicked something in the screen with your mouse. And that's still the case today, that it is kind of a separate thing. You need to, in your applications, support more than one API in your code. some call to do that stuff, to interface with the rest of the windowing system, which tends to be very system dependent, right? Your Windows applications look quite different from your Mac application than from your Linux application. There's some cross-platform frameworks for doing windowing. They're still having to solve that problem on a platform-by-platform basis. They're just providing a higher level interface. And then from that, you would then specify, here's the OpenGL context that goes with that particular window. Only once you've done that, then can you start actually doing OpenGL calls and start to render things within that window. So in the very beginning, OpenGL 1.0, back in, I guess, 1994, the term that you hear used, and it's still valid, is pipeline was entirely fixed function. Fixed function means that all the operations of OpenGL, they were fully defined, and the application could only really modify, you could think of it as some basic state configuration variables associated with that fixed function operation. So the actual math, if you want to think of it that way, or if you want to think of it, what would the VHDL have looked like for this implementation of the OpenGL 1.0, something that was compatible with that, would be entirely fixed. There's no programmability there. What there was just configuration. In fact, that was why the API kind of looked like this back then. I wouldn't actually be changing anything that's going on in hardware when I would specify GL color red versus GL color blue. The actual implementation really depends, but you can think of it as I'd be changing some register. So some sort of register would get changed that would hold current color information in it, and until that gets changed, all future vertices would be associated with that current color information. And so the math that it would be doing would be really fixed as well. It would, doing a lot of the same steps we do today, which is read in the input vertex data, do some geometric transformation of it that we will talk about soon, do the rasterization, blend all your colors together, and get your final result on the screen there. Fixed function doesn't mean that it's bad or anything like that. It just meant it was fixed. You couldn't reorder the set of these operations for a given scene. You always had to first specify your vertex data, then do a set of transformations, then do the rasterization. And it was configurable but not programmable, I think would be the right way to say it. You could set certain parameters of that operation. You then feed it input data, but that was about it. That was the main API interface to the hardware here. That pipeline actually continued to evolve over that next decade through various OpenGL versions, from that 1.0 through version 2.0, but was still based on that concept of fixed function, where you were just specifying your input data and specifying configuration information for it. OpenGL was and is still commonly referred to as a so-called state machine, where the functions in the API were there to either provide input data, here are my vertices I want to now render and correspond to my next scene, or if they didn't provide input data, they modified existing state variables. And think of those as registers if you're thinking about it from a hardware perspective. And then how the input data got rendered was that direct function of the state variables. Despite having all sorts of, nowadays, modern, more programmable features, we're specifying actual software programs to do our rendering for us. A big chunk of that red book is still about accessing, querying, modifying those internal state variables associated with the implementation. I think oftentimes in computer electrical engineering, we think of state machine as like finite state machine. We think of CPRE 281. We think of the diagrams we're drawing here. I don't think that's the exact right context that it's referring to it here when people say that OpenGL is a state machine. State, I think here refers to the configuration of the current render we're interested in. So it is a machine that processes based on a state. It is probably also, philosophically, also a state machine that has a finite number of states associated with it, but it doesn't imply that it's just a big bubble diagram that's being implemented in hardware for fixed function VHDL. There's a bit of semantic argument there that ultimately all hardware is that. It's just a matter of how many states and how we describe all those states. But when someone says that OpenGL is about a state machine and we're interfacing with this state machine and that is still used quite a bit, maybe the term you want to use is like configuration data. What is the current configuration of the current scene and how we're rendering things in our scene? And that is still, despite all the modern features, a big chunk of the OpenGL API. So you go to that red book, you look at Appendix D, which is just the listing of the state variables that you can query or modify via API calls, that's still 90 pages long. So that's a lot, right? I mean, just to implement those and to understand those. The defaults, fortunately, get us pretty far in terms of getting a red triangle that looks pretty decent inside our window. So we only are going to be modifying state variables or render configurations that are meaningful for us to modify, and we're going to leave the rest at their defaults. And it's almost as if we're not even aware of them because they're set at the default. Our hardware is built assuming that default, and that gets us pretty far. It gets us started rendering. It gets us results that look reasonably good. This is a diagram of the OpenGL 1.1 fixed function, so-called state machine. I think you may or may not be able to click that PDF. I had a little trouble opening it this morning, but here's a version of it. This is what we used to implement in CPRE 480 back in the day. Over a decade ago is how we would implement this in the equivalent class of CPRE 480. We wouldn't do all of this, just like we don't do the entire red book. We did a reasonable subset of this. It is an attempt to specify really all on one page, all the different things that were in that version 1.1 of the OpenGL standard. There's a high-level view over here. What I would want you to take away from that high-level view over here is it is an attempt to kind of show it's a different view of the same thing, but effectively that rendering pipeline still, right? Here are the main stages of the rendering that we are doing, and here's where they correspond to in this diagram here. And then if you were to look at more like specific subsets of what would be an interesting one to look at, we haven't really covered any of this yet, right? Per fragment operations, frame buffer and frame buffer control. That was down here in the lower right-hand corner. It's here somewhere. This is a big chunk of your current render output is what would be part of that. And as part of that are the various functions that allow you to change, modify, or potentially read from the current state configuration information associated with that render output side of things. So we're not doing any alpha blending, although you could. Not needed to be added for MP1, but if I asked you to do alpha blending, we could have covered that and done that in MP1. Depth buffer testing you will eventually be doing. We're doing all entirely 2D, so it'll get rendered in the order that you specify stuff right now. But basically, interfacing with the frame buffer and writing pixels to data is what we're doing right now in that component. And that was the OpenGL 1 or up to version 2 version of the pipeline there. Starting in 2.0, we officially added programmable shaders. Before that point, there was kind of vendor-specific extensions to OpenGL, and then in OpenGL 2.0 it became more standardized. So this is a pretty big change. Lots of features were getting added to the fixed function pipeline over that period of a decade, and graphics significantly improved over that period. This was the official adding of 2 programmable stages to the pipeline. Vertex shading, which allowed you to take the existing hardware that was going to do your MP0 type math, that transformation of vertices, and allow it to now be also programmable as well. And then fragment shading, which we could still do our fixed function render output type of shading, but then we also can have some programmability on top of it. I guess the nice thing about this era is it supported both. So you could do both the new programmable shading for a particular scene. You could also always fall back to the fixed function pipeline as well. So both were available in that stage. Yeah, sure.
I think I'm still a little confused on the difference between being programmable and configurable. Could you?
And maybe it's a bit of semantics, I guess. Let me see if I can, an analogy that's like direct to what you're doing right now. So conceptually what I mean by that is, let's say you have a piece of hardware that does matrix vector multiplication, right? A configurable version of that hardware would allow you to change what the matrix is. But no matter what, it's always just doing matrix vector multiplication. A programmable one would be one in which you can take the same multiplier and adder hardware and do an FIR filter with it. Something fundamentally different. At some point, programmability is configuring muxes in a configure. You know what I mean? It is ultimately kind of at the end of the day the same thing. But that's my distinction. One is I'm changing some constants in my design. I guess they're not constants, but I'm changing some parameters of my design. I always want to add 7 to this value when it comes in, but I can change it to add 8 instead, and that's how I configure it. But if instead of adding it, I want to take sine of x instead, That's now a programmable, version of the same. Is that
Yeah.
okay? And I do kind of conflate the two a little bit in this class because I do think it is easier to talk about OpenGL with this like fixed function pipeline and to talk about the algorithms of what are happening because that really hasn't changed. How we do this flavor of rendering hasn't really changed with programmability. We just have a lot more flexibility of what we can do because we can specify that via software versus interfacing with a fixed piece of hardware that can do one class of things and do one class of things relatively well. Let's continue with the evolution and then we can talk more about some of what that means in practice. Starting with 3.0, OpenGL started to introduce the deprecation model. This is also where the standards started to become, I think, a bit of a bifurcated mess. Writing graphics applications starting in this era, you have to really query what system you're running on, what driver you're running on, and what version of OpenGL does it currently support. Because now it was no longer, we try things and we fall back on what we have. Now it's, some of my code's just not going to work depending on what class of hardware I am running on here. And you'll see we kind of hide away those details, but a big chunk of the boilerplate code we have in any OpenGL application is basically a set of functions that determine that information for you. What are my capabilities of the hardware? What can I do? What of these, 300 pages of API calls, which of these can I actually support, which ones can't I support? We do that at the beginning of every single OpenGL application. This is where there was kind of a full kind of split where you had some drivers and some software applications and some hardware that could support everything still. So all your old applications would still work, and others that decide to say we're going to go only with the forward compatible mode where you only have programmable shaders, you're not supporting the old fixed function hardware. It's still kind of a funny thing though. I tried it, it was a couple months back, on these relatively modern Cougar 2050 systems that are running OpenGL 4.4, 4.5, something like that. Pretty up to date in terms of graphics hardware, latest NVIDIA drivers. And everything I have read indicates that it should not support fixed function OpenGL. It shouldn't support my first triangle example on that previous slide. Still works though. So some magic is happening in the driver, or maybe NVIDIA has just decided it's just easier for us to keep supporting it. The hardware wouldn't support it in the same way. The hardware wouldn't look like this anymore underneath the hood, but there's some software translation that's taking the fact that there's no shader being provided and it's creating some sort of same default shader that does what it needs to do. So everything I've read said it shouldn't be supported, it should not work. Just a couple months ago it still worked. I don't know, we tried today, maybe it doesn't work anymore. But this is definitely where things started to get a little bit bifurcated in terms of what either your hardware could support or more importantly what your driver could support here. And then starting in 3.1, the idea was that once you're 3.1 and above compatible, you're kind of removing that option to use the fixed function pipeline, even though it seems like drivers still to some extent kind of support it for you. The other difference, and this does change how we interface with it, we no longer specify vertex data as state information any longer. That GL color call is no longer something that would be valid in this mode of things. Everything is going to be GPU resident. So a big chunk of my OpenGL code now is setting up these buffer objects and transferring buffers of data over to the GPU at any one given point in time. For the most part, this semester, this class targets OpenGL 3.1 compatibility. It's not fully compatible. It would have to support the whole red book to be fully compatible. And sometimes we tick a couple features that seem cool of more recent APIs, and we support that as well. But as I mentioned, I'd still like to use the fixed function way to describe certain algorithmic techniques because I still think it's easier. It's easier to describe things using fixed function OpenGL. We deal a lot with the mechanics of OpenGL once we're in 3.1 and above. I'll go quickly through this, starting in 3.2, and now we're getting to more recent time. There's now a third shading stage, those are the so-called geometry shaders. That sounds similar to vertex shading because they both have to do with geometry. Vertex shaders look at individual vertices in isolation. I've specified this XYZ location with some attribute associated with it. What do I want to do with that information? Do I want to move it? Do I want to change it? Geometry shaders deal with whole primitives or whole meshes of primitives at a time. They allow you to specify higher order objects than just things that are composed of individual triangles, allow you a little bit more of a geometric specification for what's happening in your scene. They're kind of weird, they're kind of complicated. We don't implement them in the lab, so we won't talk a ton about geometry shaders. There's also computation shaders as well. And then here I'm talking about tessellation shaders that allow you to take existing geometry and subdivide it even further. For the most part, although you have 4.6 version of OpenGL, we're going to stick with that 3.1 view of the world in which we still have a lot of fixed function hardware here. It's not truly an accurate kind of split of where fixed and programmable is, and part of this is really implementation specific. But if you look at this picture, I think it's fair to say purple is programmable, and then that dark navy blue is our fixed function hardware. So we're still implementing both. I would say what you're doing in MP1 is very much just fixed function hardware, right? It's state values. You're specifying things like, going back to your question, viewport size. That is, it's an API call, it's GL viewport, that's still part of the OpenGL spec. You are then setting some registers in your design to say, hey, I'm doing the same math every time. Here's my xmin, xmax, ymin, ymax, zfar, znear, and you do that same math no matter what. So for us, that viewport calculation is still fixed function. Likewise, where we stop being fixed function and where we start being programmable for this is not as clear, but for right now, it's entirely fixed function. We have a module, this render output, that takes in these now fully processed, now converted to fragments because they were just all points originally, and we're calculating what color they should be and where they should go in the frame buffer. That's entirely fixed function. We can get pretty far with just fixed function once we want to start doing some more fun things where our hardware doesn't change, but what we're doing is entirely just changing via our software applications. We will start working with shaders here. Other point I want to mention is the term shader is also a little ambiguous in graphics parlance. It refers to both the programs we write as well as the architecture, as well as the processor itself. So my hardware, and it's a little annoying to even use the term correctly, my hardware has something capable of doing vertex shading. It is a vertex shader hardware. And certainly for ours, we're going to be building a little mini 381 style processor that is a vertex shader. It's going to have its own ISA, it's going to have a set of instructions it's going to be supporting. It is a vertex shader. The program is also called the vertex shader. The whole task of rendering is also times referred to as shading. So you hear the term a lot. The nice thing is you'll never be using it wrong because it all is using the same term there. But we're doing both. So vertex shader is the piece of hardware that is doing shading. And then the name of the program it's running is also called a vertex shader. So to compare to the OpenGL 1.0 era state machine, this is the OpenGL 4.0 state machine. They don't call it here, they're calling it the pipeline map. And it's a nicer diagram. So the tools for drawing diagrams over that 20-year period have gotten a lot better at the very least. You can also, you definitely have to squint at it a little bit more. Okay, there's just a lot more going on. So we've added more features, there's more complexity here. If I were, I think it's this one, it's in the lower right-hand corner, but let me just double check here and let me zoom in a little bit. It still has that kind of render pipeline view of what is possible here. Actually, this is referring to what are the operations it supports. So the render pipeline view, I think, is these outermost blocks that are still kind of showing. Oh, it's at the top of this diagram. I just missed it. This left to right diagram is still that rendering pipeline. So that hasn't really changed. And now there's just a little bit of color coding as to where that actually corresponds to in the underlying implementation. And some of that is still, I would say things here, some of that is still going to be relatively fixed function. This, they call it vertex invocation, and I just called it vertex fetch, whereas they're referring to vertex fetch as something different. I think it's effectively the same thing as what we already have in there. Given some specification of what the set of objects are going to be in your scene, grab not just XY location, but all the information associated with those vertices, and then assemble them together here. To me, we kind of combine that all into vertex fetch. So we have just a bunch of information associated with each vertex. The difference is our implementation limits it to just 4 attributes for vertex. Maybe it's a lack of creativity, but I wanted to keep like the physical FIFO as something meaningful, whereas this, there is effectively a software process to grab an arbitrarily sized vertex here And then there's that step that's going to be doing vertex shading, and that's going to be some sort of processor running some sort of code associated with that there. And then we can look at the render output side. This is going to be called fragment processing here. And right now, for better or for worse, we are not really doing any of this in our render output. The stuff that we are doing here would be kind of right here, where we have a pixel. We now want to actually send it to some location on the screen. That is the output of that separate process, that separate program that eventually will be running called fragment shading here. So they're different. If you were to, and I don't expect us to be able to do this right now, grab these two PDFs, they're both on Canvas, kind of look side by side, a lot of the same stuff is still there. The kind of state information we're specifying about what we're doing in the render here, depth function, that's still part of OpenGL. Different ways we interpret depth in a scene for different purposes. That should still be part of, now that I said that I should check that, that should be part of our depth testing here, where we specify depth function associated with the shading that we want to do here. But it's not showing all the, so GL frag depth, that's the attribute, that's not the function, that's not the state information here. So they're different. There's been changes over time. There's been much more functionality that's been added, but they're not terribly different. And we're going to be implementing a relatively small subset of that. Every little box in here, certainly every large box would be a separate lab, but every little box in here would be like one person's time spent trying to implement that particular feature of the API. Question?
So like, if you, like, I guess, what does that mean, like, practically, that it's not fixed function anymore? Like, I guess I'm having trouble wrapping my head around that.
Well, part of the reason is because we haven't talked about what's happening in these states. I think that's why it's not that clear. What does it mean to not be fixed function anymore? If I go back to this initial diagram, this one, where everything is fixed function, there are a set of stages that is part of our rendering pipeline, geometry, and doing rasterization, doing texture mapping, and doing kind of render output kind of steps, fragment operations at the very end. That has not changed. There's things that have been added on top of it, but that has not changed. The fundamental steps we have to do to get from an XYZ red vertex and a set of them to a triangle on our screen at the end of the day. So that what is needed to be done from a logical perspective has not changed. When we have fixed function hardware, what I call the old CPRE 480 design, we had a module, let's ignore lighting for now, that would do vertex transformations, that would take the incoming XYZ value, and we'll see that there's a matrix vector operation that happens on it. That was fixed function. There was a module that did matrix vector multiplication, and that's all that it would do. You could configure it. What you can configure it via is by changing what the matrix is. And we'll learn about this. As we change the matrix, you stretch the image, you shrink the image, you rotate the image. You can specify all that via a set of linear transformations. You can get a 4x4 matrix out that does exactly that. Takes an input XYZ value, moves it somewhere else. By moving a set of 3 values, you've stretched the triangle, you've done all sorts of things to the triangle, you've rotated it. That's what that hardware would do. That's fixed function. So your OpenGL code, your code was about, I specify the vertices still, I also have to specify what my matrix is. I think the call was called GL matrix, but it was something like that if it wasn't exactly called GL matrix. It was something like that, where you would literally configure it to say, change my matrix. Until I tell it to change again, every vertex that comes through gets that transformation that happens here. Now with programmability, and I think this diagram is sufficient for that, that step became programmable, which is to say, I'm still specifying a matrix somewhere. But now I'm running a piece of, you can think of it as assembly-like code, but there's C flavor of languages, and there's multiple of them that allow you to specify this, that I'm writing a piece of code that determines what I want to have happen to my input vertex. By default, unless we want to do something different, you'd actually want that code to do the same exact thing. Do matrix vector transformation given an input matrix and spit out my result. So it doesn't look that different at first glance, but it's programmable code. It is a piece of software, either assembly or some higher level software specifying what I want to have happen at this stage. We could just do the same matrix vector multiplication. We could do all sorts of things.
So the difference is
Yeah, that's one way to look at it. And so our calls in OpenGL look a ton different now. Now it's about specifying, and this is why modern OpenGL, it's very wordy. There's a lot of things you have to specify just to get a single red triangle to work now. Specifying, here is the vertex shader source. And literally, you have to read it from a file, or you can just specify a set of strings. I need to actually compile that source. Your program itself is calling a compiler that the driver would have to support to get a result. We'll be writing that this semester. I now have to basically link and build an executable to run on the GPU. So it's doing all those steps of program specification, compilation, linking, and execution. Now I can specify my matrix, where my matrix is now just an input to that program. So it's all those steps, versus in the past, there was no program. You do this matrix operation, I specify some configuration information associated with it. Yeah.
So is that pretty much what's happening with the like big pixel shader we have in MP1?
I haven't looked at it. Let me see if I can humor me for a second. Let me see if I can open it up. This would be in the MP1. Well, I may have it somewhere different. So yeah, software common, the shaders that are in there, right? What do we got? So this big points.vert. Okay, and there's also, let's look at both of them. Let's look at pass-through.vert. My text editing isn't working well, so this will have to suffice. We will cover this, by the way, so don't assume that you have to understand all of this right now. On the left is what I would call a pass-through shader. It's actually not even doing what the fixed function hardware would be doing, because we haven't implemented the hardware for that yet. So on the one on the left, this is a so-called pass-through shader. And for better or for worse, depending on which version of OpenGL you are compliant with, the syntax does change in very small ways, not in any big ways, but here, I'm sure I had a good reason for specifying that this was OpenGL 4.3. I guarantee you I had a good reason. I don't remember that reason. Specify OpenGL version 4.3 for this shader here. We then specify this shader, this piece of software that's running on our piece of hardware, should be expecting input vertices that have 2 attributes associated with them. It should be expecting at location 0, the first attribute, a vec3 vector of data that specifies XYZ information. Should also be expecting a second attribute that's also a vec3, an RGB information that we call color here. Now, in reality, in our hardware, they're actually not vec3, they're vec4s. You've seen those data types in that SGP types. I have that hard-coded in our design and consequently in the driver as well. We have a 4-wide vector for position X, Y, Z, and W, which we're not going to use right now. We have a 4-wide vector for color, R, G, B, and A, which we're also not using right now for alpha. But this should still work. As we run this shader on our modern hardware running on this particular system here, we only need to specify X, Y, Z. Our hardware is expecting a 4th value. That that vertex fetch module that is already there for you will figure that out for you. It'll grab you 4 values and pass it down the pipeline. It also specifies an output location. Here, location 0 is kind of by default in this version where you specify, and this is part of the spec, vertex shader has to, if nothing else, specify an output location. That's kind of a given. You can also specify all sorts of other attributes as well here. So layout, location 1, output vector, v color, it's just specifying it, and then there's actually no math happening here. Given my vec3 xyz, append a value of 1.0 for w, that's an output value. For my color, take my input color and specify 0 alpha, so full opacity for that. For your MP1, and this is why it's not going to look exactly the same on your workstation as it is on your hardware attached monitor. It is still just doing a pass-through, but it's also specifying, I would call this a piece of configuration information, not something programmable, that I want for the individual points I'm passing through to have a little bit of width associated with them. My guess, how this would be implemented in hardware, because we don't implement this in hardware. You could do this for a project if you wanted to. When we get to the render output stage, we take a look at that information of GL point size. So these fragments that I'm wanting to send to my frame buffer have a certain radius. I assume that's what that's specifying there, of or maybe that's diameter, of how many pixels they should each correspond to. We do it for us so that we can see it, right? That's the main reason we have it here. I don't know, do I even have Sierpinski, for example? We do that so that we can see it. Otherwise, it's hard to see pixels on a workstation, single pixels on a workstation display. It's just, if you're drawing one, right, one of them is called the red pixel, right? You're not going to see it if it's just a single, or depending on your vision, maybe you can see better than I. You're not going to see it if it's just a single red pixel there. That one is running bigpoints.vert. If you're willing to humor me, we can mess around with this all sorts of ways. So right now, we're passing an input color, and everything is green. This is in the vertex shader. The fragment shader is probably doing very little. We could mess with the color if we wanted to. That program specified some greenish looking pixels. If we wanted them to be red instead, how do we think we would change this call? You can hazard a guess.
At each number, link in a row.
Something like that. I think this is the same shader this application is actually running. I don't have them open on the same screen. This is, well, I gotta make sure it's actually running the same one. So common shaders, bigpoints.vert. I mean, this could be just I'm not in the same directory here. One second. This is a different directory. We are in different directory. So I just messed that one up for you guys. That is in your directory. Let's change that back. No, only if you were going to do like an update would you have seen that. So that's fine. I'll just change it back. That's fine. I just was editing the wrong one. So that one was in like an exercise, a separate exercises folder. I had it there. So that's just put it somewhere else so that I can mess with those and not break your stuff. This should be the one that's running. Let's try it again. Thank goodness. Okay, so now, it's a little interesting. I mean, oftentimes when doing modern graphics applications, we don't specify color at all. We'll be specifying light sources and material properties, and we mathematically calculate the color versus specifying the color. But if we were then to look at the code for this, I didn't want to get into all of it yet, but let's do it because I think obviously you're interested in how does this work in practice, right? This is MP1, this is Sierpinski. Let's open it on this window so we have them side by side here. So don't make fun of my mediocre Vim skills here. Okay, software source MP1, and that was Sierpinski. Let's copy. Let's keep it back up so I don't break it when I accidentally put that in the repository. Hopefully you've looked at this code or the red pixel. They're all basically the same, right? The only difference is what pixels were specified. Today, in terms of our time available today, I don't want to go into all the details of what is happening here. We do have to do that. That is important for us. Not for MP1, but eventually to understand it. But as part of our OpenGL call, there's this call, and this is not an OpenGL function. This is like a helper function, load shaders. So we're interfacing with a programmable GPU. That load shaders is a helper function that's doing GL shader source, GL compile. It's doing all those steps for you so that your code just isn't super long here. And it is loading as a text file, bigpoints.vert, this file that we have open over here. It is loading it. It's also doing some math to calculate what all the various colors should be, but it's all the locations in the XY space, but it's also specifying as part of that, here's the initial color. For each of these vertex values, this is generating a set of buffers, or just a set of arrays in my program that are specifying for every point I have in my program, here's an X, Y, Z location associated with it, and here is an RGB color associated with it. The code is a little messy, but that's all that's doing. It's For the number of points I want to specify, I have this big of an array, and it's 3 times the total points because it's an RGB or an XYZ associated with each entry we have here. I had just some, this isn't OpenGL code, this is just C code to generate those values. And then I buffer that data over. I say, hey, by the way, I have these vertices, they have 2 attributes, and I'm going to send them over. And actually, for these calls, I could have just done it once. But this call then says, given those vertex attributes you've sent, because it doesn't change in Sierpinski, right? It's just a static set of attributes, but we copy them over each time. But for this set of points that you've already copied over to memory, draw it based on those points using this program that corresponds to the vertex source and the fragment source specified in those shaders. But we don't have any of that hardware yet to do anything with this program. Your hardware and your driver ignores that call. It gets a call to GL use program, and it traps it. The API trace that we use to trap all the OpenGL calls does catch it, and maybe it even prints out like saw GL use program call or something. It doesn't do anything with it. It just passes it on and doesn't do anything with your side. So the question then becomes, I think it's a valid question you should be asking, if not now, certainly for MP2, why does it still work in hardware, right? We have our workstation running modern OpenGL with shaders that we're specifying, and it's doing some shader stuff. It's doing some programmable stuff here. It's not doing a ton. Setting point size, and it's changing the color to some red value for some arbitrary reason. And we could do all sorts of things. We could mess with the position if we wanted to. The thing is, we don't have a lot of interesting inputs here, so we could mess with the position and make it look really bad, but I don't think we could make it look. We could try. I mean, why not, right? We could do .y, flip x and y. I mean, I'm trying to think of something we could do that's like different, right? There isn't any other variables associated with this, so there isn't that much we could do here right now, but we could flip x and y. Should still work. Now, we just changed the shader. We're not even recompiling the application. Only the shader has changed. There you go. It got flipped on its side. I mean, I'm struggling to think of like interesting things we could do with just very simple shader that we have here. But we flipped it on its side, even though we didn't change the OpenGL application at all. Why does it still work in our hardware? Or hopefully by Tuesday, why does it still work in your hardware? Well, the answer is that we really are limiting what shaders we're running. Pass-through or default shaders. These changes we've made here will not work on your hardware, right? This is a shader that flips X and Y location and sets the color to red, fully red, no matter what the input attribute said the color should be. In fact, right, we kind of ignore the whole input attribute color here. You have a piece of fixed function hardware called either viewport or render output that has no idea, no knowledge that this XY has been swapped, has no knowledge that RGB has been manipulated as well. So the answer, like, how does it work even though we don't have this, is it doesn't really, right? It's only working because we're writing shaders that are doing as little as possible, that are touching the state of our vertices as little as possible as they go through. Only once we ourselves start to implement our own shaders can we then start to write some fun shaders and see it potentially working in our hardware as well. There's a little bit of a disconnect, and we can end things here with that. And the main disconnect is we want to learn a lot of, I think, interesting graphics processing features. How do we manipulate our vertices so that we're rotating our triangles and stretching them and doing all sorts of things? All of that is implemented via shaders these days. There will be a call, it used to be called MVP transform, but basically you would specify a matrix. I'm sure I have an example here in our shaders directory. Yes, I called it MVP transform. Model view projection transform, where we specify, it's like a configuration variable, kind of, right? The matrix we want to do the multiplication by, and every time through, we actually do that multiplication. So there is a matrix vector multiplication we're specifying in our shader code. When we start to implement that in hardware ourselves, we'll start to run that shader on these. But I think we'll want to learn the techniques for doing a model view projection transformation first. So we'll learn about the math, the algorithms, the maybe fixed function way of doing it so we don't have to worry about implementing this. and then eventually you get a chance to implement it. So it's going to start to be a little bit of a disconnect there. We'll learn techniques, we'll learn a little bit of theory. The math is, fourth grade level math, we'll be okay there. But then in terms of implementing in the lab, it's going to take us a little while to catch up, because just getting very basic stuff working is taking us hopefully a good chunk of your weekend between now and next Tuesday. Let's leave things here for today. I want to talk more about OpenGL. It'll be next Thursday, but we can pick it up after demo day on Tuesday as well. Please put in some effort. I want to have a fun demo day, and it's more fun for everybody when it's working. So please put in some effort between now and then, and I want to see some great results. Let me know where I can help as well.